This is Ms. Park, and in this video we will be going through a very useful tool for algebra called area models. I hope you will enjoy it, and I know that you will be able to apply it to many things as you go through your math in high school. So first of all, what is an area model? I'm just going to draw here a rectangle. Literally, there's the area model. An area model is a way of representing multiplication, because if I want to find the area of a rectangle, all I need to know is the dimensions of the rectangle, and then I can figure out the area inside. So when we're drawing area models, we're not going to worry about scale, how long things are. Sometimes our side lengths will be negative. We'll have to be okay with that. And just remember that it's a rectangle and that the area is the length times the width, whatever they happen to be. So I'm going to go through lots of different applications. First of all, we'll start with straight up multiplication with numbers. Then we'll go to expand and simplify, which is usually two binomials multiplied together, which is a grade 10 skill. Then we're going to go into factoring, also introduced in grade 10. So we'll have common factoring, simple trinomials, complex trinomials, and difference of squares. Then we will move on to completing the square, which is also grade 10 topic. And then we'll jump over to division of polynomials, which is generally done in grade 12. So I'm going to start with multiplication. So let's say I want to know how much is 8 times 5. So 8 times 5, you can think of it as, this is multiplication. So 8 times 5, you can think of it as a rectangle with dimensions 8 times 5. I'll just make the 8 the longer side, not that it really matters. And we know how to do this in our heads. We know the area is 40. But what if I did something with bigger numbers? What if I wanted 8 times 35? So how much is that? Well, I can represent this in an area model too by saying this is 8 and this is 35. But 8 times 35 is not an easy multiplication. So what we'll do is we'll split up the 35 into two parts, 30 and 5. And so now, by splitting it up this way, I get two smaller rectangles, but I know that the area of the large rectangle is just the sum of the areas of these two. So these areas are actually easy to find because 8 times 30 is just 8 times 3 times another 10 because it's 30, and you get 240. And 8 times 5 we know is 40. So our total area is 240 and 40, which is 280. And that wasn't bad at all to do with without a calculator. So now what if I wanted to get more complicated and I wanted, let's say, a 2-digit number times a 3-digit number. Sorry, a 2-digit number times a 2-digit number. Well, what's going to happen is I'm going to want to split up my 37 the same way I split up the 35, but I can do the 83 as well. So here's my 37 split up into 30 and 7, but I can do the same thing with my 83 and split those up into 80 and 3, and that gives me this kind of rectangle that's split up into 4 smaller rectangles. And that's because when we multiply numbers, there's actually different multiplications happening. I have to multiply the 7 by the 3 and the 8, the 3 by the 3 and the 8, and so on. And that is going to result in 4 different multiplications. So what's going to happen is 80 times 30, that's 24. That's 8 times 3. But there's another 10 for the 80, another 10 for the 30. 80 times 7 is 56, but there's another 10 because it's 80. 3 times 30, well, 3 times 3 is 9, times another 10, and then 3 times 7 is 21. And now all I have to do is add up these numbers. And you'll notice that even though it looks like a lot of numbers to add, it's actually pretty easy addition because most of the numbers here are 0. 0 plus 0 plus 0 plus 1. 6 plus 9 plus 2 is 17, carry the 1. 1 plus 4 plus 5 is 10, carry the 1, 3071. And that was pretty easy without a calculator. And we can extend this to do 3-digit numbers. So maybe I won't do them, but you can. Let's say like this. It's very simple because each one can be split into 3 parts. And so I have 240 and 5. And then 190 and 3. And even though there are 9 multiplications, they're really not that bad because all you have to do is multiply the leading number. So this will be a 2, and then add up all the zeros. So 2 and then 4 zeros. Like that. And so when we're adding up the numbers, we're really adding numbers that have tons of zeros, so the addition is not bad at all. So that's where the area models can be really handy for multiplication. Well, we can extend this to algebra. So let's say I wanted to multiply 5 times x plus 2. Well, we know from distributing that this is really 5 times x and 5 times 2, which is 5x plus 10. But how does that look with the area model? Well, I'm going to make the rectangle where the dimensions are 5 and x plus 2. I can split this x plus 2 the same way I split the two-digit numbers before, and then work with the individual smaller rectangles. So 5 times x is 5x, and this one over here is 5, it's a 5 by 2, so that's going to be 10, and that's how I know that this is going to be 5x plus 10. Well, if I can do it with a 1 by 2, I can do it with a 2 by 2. So let's extend this to multiplying binomials. So let's say I have x plus 3 times x plus 5. Then all I have to do is split up the x plus 3 into 2, an x and a 3, and split up the x plus 5 into 2, an x and a 5. And now fill these in. Now we know what x by x is because if we have a square and each dimension is x, the area is x times x, which is x squared. Think about area being length times length in a square. So if the first one is centimeters, the second one is also centimeters. When you multiply those two, your units are centimeters squared. So that's why we have x squared. Now this box here is 3 by x, so that area is 3x. This box is 5 by x, so that area is 5x. And then this last box is 5 by 3, so that area is 15. So here comes our expand part. X squared plus 3x plus 5x plus 15. That's the expand part. The simplify part is that we're looking for like terms, and I see we have like terms. So this is x squared plus 8x plus 15. And this is what's known as simplify. So when somebody tells us to expand and simplify, they want us to do the multiplication to get rid of the brackets, but then they want us to simplify by collecting all the like terms. And we can do this again with any letters, with any coefficients. We can go like this, 8a plus, I don't know, 3, right? And I make the area model. I can do this very quickly. Okay, so 2a minus 7. It doesn't matter which one goes on the side and which one goes on the top. It doesn't matter if some of the dimensions are negative, like this negative 7. That's totally fine. 2a times 8a is 16a squared. 8a times negative 7, so I'm going to do the 8 times negative 7, negative 56a. 3 times 2a is 6a. 3 times negative 7 is negative 21. That's my expand. 16a squared minus 56a plus 6a minus 21. And here comes my simplify, 16a squared minus 50a minus 21. So we've just taken care of multiplication and expand and simplify. Okay, let's look at factoring now. So with factoring is the opposite of expanding. So with factoring, instead of being given what to multiply and coming up with the answer, we're given the answer and we have to think about, well, what would be multiplied to give that? In other words, if I had an area model, I'd be given the area and I have to think about what goes here and what goes here. So the first thing to do is to think about what number or what term divides evenly into both of these. So it turns out that the one that divides evenly into both is a 5. So I know that one of my dimensions is a 5. And to figure out the other dimension, I just have to split this into two parts just like I did before and say, okay, this rectangle, the area is 5x. One of the dimensions is 5. What does the other one have to be? Oh, well, it has to be x. And this one, the area is 10. One of the dimensions is 5. What does the other have to be? Well, it has to be plus 2. So that means we can factor this into 5 times x plus 2. And you can see this is factored because it's something times something, which is what we need for factoring. Okay, let me factor now. Maybe something a little bit more challenging. So we'll do another common factoring. So let's go 3a squared b cubed minus 12ab plus a squared b. Okay, what we have to do here is we have to look for the greatest common factor. Turns out that the greatest common factor from the numbers is a 3, from the a's is an a to the exponent 1, and from the b's is a b to the exponent 1. So I'm going to make my area model, and I'm going to write 3ab. And over here, I'm going to have 3a squared b cubed. Oh, I'm sorry, it's in the wrong spot. So I'm going to erase it. No, it's not letting me erase. Never mind. 3a squared b cubed minus 12ab plus 6ab a squared b. And I'm sorry for this mess I'm making. For some reason, my eraser is not working. So 3a squared b cubed divided by 3ab. Because we're trying to find out what does 3ab multiply by to get 3a squared b cubed. So I know that there's already a 3 there, so I need to multiply by 1 for the number part. The a would have to be multiplied by an a to get a squared, and the b has to be multiplied by a b squared to get b cubed. And then the negative 12ab, well, that's negative 4. And a is already there, and b is already there, so that's it. And the 6a squared b has to be multiplied by 2, so 3 times 2 gives us 6. This is an a squared. I have an a, so this has to be an a. And then there's a b, and I already have a b, so that's it. So that means that I can write that expression as 3ab times ab squared minus 4 plus 2a. And now you see how to use area models for common factoring. But what if I had a different kind of factoring? What if I had a simple trinomial? So let's have a look. So with a simple trinomial, I'm going to remind us how we multiplied. So when we multiplied this, I'll do this one. When we multiplied this one, what we did was with the area model, we put the x here and the 3 here, the x here and the 4 here. We filled in the boxes. And we got that that's equal to x squared plus 3x plus 4x plus 12. And then when we collected the like terms, we got this. So essentially, the two numbers that are at the end of the bracket, when they're multiplied, they're going to end up in this box right here, because that's where you have number times number. And the x squared, x times x, is going to end up in this box here, because that's when you have an x times an x. The other two terms are just x terms, and when we add them up, we're going to get 7. What happens with factoring is that we're going to go backwards. And instead of being given the two brackets, we're going to be given that the area is x squared plus 7x plus 12. And we got to figure out what goes around it. So I'm going to draw the area model. I know that the x squared has to sit here, so this must be x and x. I know that the 12 has to be here, but I just don't know what goes there. Now, obviously, I've just done this question, so I know it's 3 and 4. But if I didn't just do this question, I would say, well, what two numbers multiply to give 12? Oh, I know, 2 and 6. So I'll put a 2 here, and I'll put a 6 there. And I'll try it out. This would have to be 2x, and this would have to be 6x. So that would be a 2, and that would be a 6. But let's see, 2x plus 6x don't add up to my x squared plus 7x plus 12. These two terms have to add up. These two terms have to add up to 7x. So that doesn't work out, so I'm going to try it again. So I'm going to make a new area model, or if my eraser worked, I would just erase these ones, but I can't. So my x squared goes here, my 12 goes here, my x goes here, my x goes here. What else could go in these spots? All right, well, 2 and 6 didn't work. Let's try 3 and 4. Well, that's 3x and that's 4x. Oh, look, that does add up to 7x, so that's good. So that means I can factor this as x plus 3 times x plus 4. Okay, so it does take a little bit of trial and error to factor using the area model, but it saves all the writing of decomposition. And also, it explains to us why the factoring works. These are the 4 parts of the multiplication, and we have to have all 4 parts. So it's a nice visual representation, and it helps us to not forget any steps. Let's do a complex trinomial. So let's write factor. Let's just make one up. Let's go 2x squared plus 7x plus 3. And I am keeping them kind of simple just for the purpose of going quickly through the video, but this will work for any numbers that you want. The more complicated the numbers, the more trial and error you might have to do, but it'll still work. So for this one, I know that my x squared term is going to sit here and my 3 sits there. There's not a lot of choices for this one. To get 2x squared, the only way to get it is 2x times x. Not a lot of choices. To get the 3, the only way to get it is a 1 and a 3. And I can choose either the 1 goes here and the 3 goes here. I can put the 1 here and the 3 here, and let's test it and see. If I do that, I'm going to get 2x here, and I'm going to get 3x here, but when I add them up, oh, look, they don't add up to 7x. So we're going to do it again. 2x squared and 3. I don't have many choices here. Instead of 1 and 3, I can do 3 and 1. Let's see if that works. So this is going to be 2x by 3. That's 6x. This is 1 times x, which is x. Oh, look, it does work. So that means we can factor this into 2x plus 1 times x plus 3. Okay, so that is complex trinomial. As for difference of squares, let's look at difference of squares. So what we know with difference of squares is that if I had a difference of squares, so you know that it would look like this. It's that a plus b times a minus b. If I was to multiply these out, what would happen? Well, what would happen is I'd have my x squared here, and I have an x and x plus 5 and x minus 5. I have an x squared here. This is 5x. This is negative 5x, and this is negative 25. These two make 0, so the whole thing is just x squared minus 25. Well, going backwards, so let me use different letters. Let's go m squared minus 64. If I do that, I'm really being given the inside, right? Given the inside, m squared and negative 64. This has to be m, this has to be m. Now for picking the two numbers, I know that the middle term is 0. There is no m term. So these two numbers have to add up to 0. Well, the only way numbers are going to add up to 0 is if they're the same number with the opposite sign. So it has to be two numbers that multiply to negative 64 but add up to 0. So that has to be negative 8 and positive 8. So that's going to be m plus 8, m minus 8. Okay, so what have we done? Wow, so much. Okay, so we did all of the factoring. It's common, simple, and complex trinomial and difference of squares. We did all of those. Let's move on to completing the square. So completing the square is a technique, algebraic technique that is done to convert standard form of a quadratic equation, standard form, to vertex form. Okay, now standard form looks like this, ax squared plus bx plus c. Vertex form looks like this, ax minus h squared plus k. And vertex form is useful because it gives us the vertex. So if this was y equals and this was y equals, standard form tells us virtually nothing, but vertex form gives us the vertex is h and k. So often we're given an equation in standard form and we're asked, what is the maximum or the minimum? Well, in that case, we need to know the vertex. So watch how cool this is with area models. You probably know already how to complete the square algebraically, but let me show you how neat this is. The whole idea is that, let's say, for example, you want to complete the square x squared plus 8x plus 9. You want to know what the maximum is. Notice that in the vertex form, we have a something squared. We have a binomial squared. So that's what we're going to try to create, something with a binomial squared. So I'm going to first try to factor this. Okay, so x squared plus 8x plus 9. So I'm going to go like this. I'm going to put the x squared here. So this is x and this is x. We know that. Okay, now these two are going to add up to 8x. They have to, right? They have to add up to 8x. But I want something squared. Well, to get something squared, it means that this dimension and this dimension have to be equal. So I'm going to need two numbers that are equal and add up to 8. Well, how do I do that? How do I get two numbers that are equal and add up to 8? Well, that just has to be 8 divided by 2, right, in order for them to be equal. So in order for them to be equal, they both have to be 4. So this is going to be a 4x and this is going to be a 4x. But here's the problem. What does this last term have to be? Well, this is a 4 by 4. So that's going to be 16. My question doesn't have a 16. My question has a 9. So that 16 is too big. Let's take away the 16 and add a 9. That's the same as taking away a 7. Right? Because what I have in here in this box is too much. It's bigger than my question. It's 7 too many. So I can write what I have as x plus 4 times x plus 4, or in other words, x plus 4 squared. That's all well and good, but it's too big. So now I have to subtract the 7. And that is completing the square. It's quite cool. Should we do one more completing the square? Yeah, let's do it. Okay, so let's do another one. So for example, I'll do x squared. Let's make it negative this time. Minus, I don't know, 12x. Okay, plus some number, 15. Okay, so I'm going to make my box. There's my x squared, there's x, and there's x. Now these two numbers have to be the same so I can write something squared because I want the two dimensions to be the same. Well, if they're going to be the same number, and there's two of them, and they add up to negative 12, then each one has to be negative 6. So this is negative 6x, and this is negative 6x. But if they were both negative 6, then that would be a 36. Well, that's too big because my question is not 36. My question is plus 15. So I've got to subtract 21 to get to 15. So I can write this as x minus 6 squared minus 21. And this is vertex form. I can see the vertex is 6, negative 21. Pretty cool, huh? Okay, let's go to the last one. So we're going to go up to grade 12 now and look at division of polynomials. And this is super cool too. And really, even if someone's in grade 10 or 11, they'll be able to follow this. So sometimes, not 12, sometimes in grade 12, we have to divide two polynomials. So I'll give you an example. 2x to the fourth plus 5x cubed plus 7x squared plus 16x plus 15 divided by 2x plus 3. And if you're in grade 12 or you teach grade 12, you know that there are lots of ways to do this. We can do long division. There is long division we can do. There is also synthetic division. And maybe even other ways, but I'm going to show you how quick this is with area models. It'll actually really, I think you'll be impressed. Okay, so what I'm going to do is remember that this part over here goes inside the area because I want to do a division. And the 2x plus 3 is what I'm dividing it by. So here's 2x and plus 3. Okay, so I know that this is going to be split like this. Now, if I have a quartic, with that means an expression with degree 4, and I'm dividing it by a linear, then x to the fourth divided by an x is going to give me x cubed, which means my answer is going to be a cubic. And a cubic has 4 terms: the cubed, the squared, the x to the exponent 1, and the constant term. So I know that I'm going to have to split this into 4 parts. That's my area model. And now I'm going to put my big expression on the inside. So this is 2x to the fourth. I'm going to start with that. And then I'm going to work my way around the dimensions. So 2x to the fourth, if one of the dimensions is 2x, the other one must be x cubed, right? But if that's x cubed, then this must be 3 times x cubed, which is 3x cubed. Let's look at my question. My question doesn't have a 3x cubed, it has a 5x cubed, which means if that big expression is going to fit inside the area model, I need another 2x cubed, right? So I can have 5x cubed. But now if that's a 2x cubed and this is a 2x, then what do I have to multiply that by? Oh, x squared. But if that's x squared and that's a 3, then this is 3x squared. But my question doesn't have 3x squared. My question has 7x squared. So I have to add another 4x squared. So 2x times what is 4x squared? Oh, 2x. But if that's 2x, then this has to be 6x. But my question doesn't have 6x, it has 16x, so I have to add another 10x. Well, if that's 10x and this dimension is 2x, then this has to be a 5. And if that was a 5, then 3 times 5 gives me 15. And look, I was able to fit my entire expression into the area model, which means that my answer is x cubed plus x squared plus 2x plus 5. Cool, huh? Let's do one more. And in my last example, the polynomial division is not going to result in a remainder of 0. There will be a remainder. So let's try this one and see what it looks like, and then we'll be done. Okay, so this example is x cubed plus 7x squared plus 10x minus 8 divided by x plus 3. Okay, so we know that this is a cubic and this is a linear. And if I'm going to have a cubic divided by a linear, my result is going to be quadratic. And quadratic is going to have 3 terms. So when I make my box, I know that it's going to have x plus 3 here. And this one's going to split into 3. So I'm going to start with my x cubed and then fill in the boxes as I go. All right, let's see how quickly we can do this. If that's going to be an x, then that's an x squared. But then 3 times x squared is 3x squared. But my question doesn't have 3x squared. It has 7x squared. So I must add a 4x squared. Well, if that's a 4x squared and that's an x, then that must be 4x. But if that's 4x and that's 3, then that must be 12x. But my question doesn't have 12x. It has 10x. So I have to now subtract 2x. And so x times what is negative 2x? Well, negative 2. But if that's a negative 2, then that's going to be a negative 6. Uh-oh. My question doesn't have negative 6. It has negative 8. So there's going to be a remainder of negative 2. So my answer is going to be x squared plus 4x plus 3 with a remainder of negative 2. And there you have it. I hope you enjoyed all of these. What an amazing tool that can be used really throughout all of the grades. And now we've completed all the examples. Please keep practicing, and thanks for watching.